Yeah, so thank you everyone for coming to AMATH departmental seminar. So today we have Qian, who is our own faculty. And this seminar in general will be our own faculty are presenting what they are working on. Hong is the first faculty that is presenting, and his talk is on applied mathematics for new thermodynamics. And we are super happy to have you, Hong.
Thank you.
Yeah.
Thank you, Ali. And thanks everyone to come to this online talk. And I'm very glad I have this opportunity to tell you a little bit of something we just done in the last 3 or 4 months. And actually is a little bit of benefit from stuck at home. So a collaboration developed out of it. Okay, so what I want to tell you is a story about how we can thinking about thermodynamics with a little bit of new, different mathematics. So here I started with a sort of hypothesis that is a little bit of new mathematics is actually needed to understand thermodynamics. And this little bit of new mathematics, I hope, will make it the thermodynamics just like the calculus for mechanics and the PDE and the linear algebra for quantum mechanics, and also the geometry for relativity theory in physics. And as some of you probably know, thermodynamics so far has not have a very high level of applied mathematics involved. And hopefully maybe a little bit of new things come out of this. And since thermodynamics is not really our sort of general applied math background education, so I start slow by actually give you a few, a very brief impression. What is it? I cannot really give you an introduction, right? Because it's a huge field. You have to take a course if someone really wants to study it. So what I choose to do is actually a 3 link on Wikipedia. So the very first link is, what is thermodynamics? And I'm just going to read the very first paragraph here. Basically, it says thermodynamics is a branch of physics that deal with the heat, work, and also temperature, and their relationship to energy and also adiabatics. And so I guess I leave this reading to you, but the important thing I want you to get is it's supposed to be very useful. And it's supposed to be deal with very complicated problem. And this is one branch of physics which has a huge impact on our daily life. But you already start to see a very interesting phenomenon is, but this is not something seems like we actually as applied mathematics spend time to study, very much in contrast to mechanics, which or many applied mathematics do feel like that is the physics we know. So how can that be? Okay, so now let me go to the second link. In the theory of thermodynamics, there is this item called a fundamental thermodynamic relation. So obviously it has to be something very important with the title, with a Wikipedia page. And it's pretty big a page. I only want you to pay attention to 2 equations. The first equation is here. This is the equation basically says, in a process, the change in energy is related to change in entropy, S is entropy, with multiplied by temperature, and in mechanical work to do with the changing volume, and the P is temperature, the pressure. And a little bit later, in a few lines below, this equation has been generalized by Gibbs, who now introduced one more term here. And this term says the energy change in the system also relate to the number of molecule changes. So the N depends on which type of molecule. And then there's a new quantity come out called chemical potential. I'm not going to say more, and you don't really have to understand the meaning of these terms. I just want you to realize there is this mathematical form in terms of du equals some variable, usually supposed called conjugate variable ds and the pdv and the mu dn. In fact, what later I will show you is the more legitimate way to write it is not du equals something, it should be ds equals something. And in that case, it is the 1 over t in front of the u. That's all I have to say about this item. Now, I'm going to go to the third item, and this is even less widely known, except some people actually taking the course. And even taking this course in physics department, some professor basically tell you this is not important, this is chemical engineer. But what is it? And here in the Wikipedia, it tells you now these quantity I just mentioned to you is related differently. All the quantity I showed you earlier under the differential now is in front of differential. And then the term in front differential now become after the differential. So now we have n d mu, s dt, v dp. And there's no du here. And then if you rewrite this a little bit, it's basically ended with having a formula. All these differential multiplied the corresponding variable equals 0. Okay, so I just want you to have this impression. This is what now currently the theory of thermodynamics, the equilibrium mathematics looks like. And now, in general, the current understanding of thermodynamics, especially its mathematics, is involve a decree called there's existence of entropy function. Or for system which many degree of freedom, you can actually be a functional. And then this entropy function clearly we all know is something to do with statistics. And then the theory of thermodynamics further stipulate that the entropy function has to be a Eulerian homogeneous function of all extensive variables. So here I want to mention a little bit of what is extensive variable. Extensive variable is those quantities, if you double the size of the system, they just double. For example, energy, volume, the number of particles. And each one of these quantity has a corresponding quantity. And that was the temperature, pressure I showed you earlier. And thermodynamics are going to be very universal, and it's only applied to a very big macroscopic system. So this is what the current textbook tells you. So you don't have to read this. This doesn't intend to use. This is just trying to tell you the previous slides I showed you basically come from these green boxes in this textbook, which is a very well-known, widely used book in physics department to teach thermodynamics by Herbert Kalman. Now, in the 1960s, last century, almost 60 years ago, there's a book being written by this physical chemist, Hill. And the title of that book is called The Thermodynamics of a Small System. The theory was there ever since, but for many years, for almost 40 years until recently, nobody paid attention. But recently, because of nanotechnology, and suddenly this theory being picked up. And there's a lot of activities, and a lot of people said this is amazing theory, very useful. But actually, if you study it, there is always a nagging question: is that we don't really understand how this theory came about. He sort of did a few magic things using the arguments, classical arguments, and then came up with a formula like this. So now he basically says the entropy should be written as this is energy, this is volume, this is the number of particles. You see the T now is on the denominator. And then he basically, and all these other terms and the relationship is classical. But he basically add a term to it. And then he said this term should not be extensive, i.e. when system getting to infinity, all those other terms S, U, V, and N should be order 1. But this curly E should be less than order 1. So therefore, in the macroscopic limit, drop it out. That's how he's now going to use his theory to describe a small system, not a macroscopic one. And then he still writes this relationship, the fundamental relation, thermodynamic relation, is the entropy change in terms of these quantities, which you already seen in the Wikipedia. What he made a improvement or difference is he decreed this new quantity he introduced, curly E, now should satisfy another equation. And you did notice that the Gibbs-Duhem equation is originally on the right-hand side equals 0. But now he says it's not. It should be equal his curly the differential of curly E. So this is now the new theory, and it's not completely clear, certainly with a little bit more rigorous requirement in mathematics, where did it come from? And even conceptually, we need to ask ourselves the question. Now, if we just study a small system, and then we don't really have all the average, the macroscopic, the traditional way to do statistics, where even a universal behavior come about? Now, so here is our approach. We don't take the standard way as the physicists or many people in this area called many-body physics. Basically, believe on treating any thermodynamic behavior of a big system has many, many, many parts. So therefore, you have to study so-called the many-body problem. And instead, we actually do taking the kind of a point of view as a mathematical physics by starting to do a piece of mathematics. And this piece of mathematics basically came from Cramér. That is, we believe the world is stochastic. We're not going to justify it. We're certainly not going to derive where the probability come from Newton's law or other things. We just basically say this is the right mathematics to describe things. Now here is for anyone taking our new department sequence on 561, 562, and 563. This, of course, is the very first beginning of defining what is a probability theory in a modern time. That is basically say, the world is complicated, many, many things can happen, and all those things can happen, you should collect them together and form a set and call this a state space. And within that state space, each one of these events can happen, but they don't happen for sure in a more complicated situation, so they happen with certain probability. And then we only observe such a system through a function on this state space. So therefore, if one of the events happened, then you're going to observe certain numbers. Now, another thing happened, you will see another numbers. And since these thing happens with probability, what you observe and you will have randomness, and this is called a random variable. Now, in this description, and now if you think about this piece of math and this kind of stochastic world, there are actually three very, very important mathematical in connection to the deterministic classical world we sort of feel comfortable with. So I want to go through a little bit detail with these three I call landmarks. That is the law of large numbers, central limit theorem, and particularly the third item, large deviation principle. And this turns out is something not every applied mathematical person sort of study, but we believe it's actually behind thermodynamics. Okay, let's just talk about law of large numbers. So law of large number states if you have a random called X, and you do repeated identity measurement of it again and again, m times, and then you do the mean value of these quantity, and if the m go to infinity, eventually this, because of these x is a random, so the sum is random. But when m go to infinity, the sum actually become a single number. That is the expected value of the random variable. Now, you can also do a different way. Instead of actually measurement and then just do their sum and average, you can ask a system, and let's just think about simple system with a discrete number of possible outcome, k equal 1, 2, 3, 4, all the way to capital K. Then you can ask, when you do the measurement again, how many times going to be k equal 1 shows up, and how many times going to be equal 2 shows up. Just think about a dice. And in this case, you can construct the frequency out of many, many sampling. And that frequency, of course, still random. But if you let m go to infinity, then this frequency converge to the probability. So now I do want you to notice this limit has some very interesting and profound consequences. On the left-hand side, these are something you can get from data. They are much more real. But on the right, they are just very, very abstract mathematical concepts. And these two relations basically tells you in the limit, this very real thing is related to this very abstract thing. And how statistics now relate to probability theory. So what is the central limit theorem? So I like to present a twisted version a little bit, even though they're completely equivalent to the standard textbook. So let's do the same sum x1, x2, all the way to xn, identical and independent. Instead of divided by m, now I'm going to divide it by square root of m. Now, of course, last time page shows divided by m, I have a limit. Then, of course, divided by square root of m, I will get infinity. Then I'm going to use this infinity, subtract another infinity, which is the square root of m times the expectation. So now you do this difference of the two infinity. And that is something usually we are not allowed to do, right? Because infinity minus infinity is very tricky. But interestingly, in this setting, it becomes a random variable with very well-defined form and shape. It is going to be a normal Gaussian distribution with a mean value 0. And the variance is exactly the variance of this 1 over the x. And that is central limit theorem. Basically, law of large number and the central limit theorem put together, saying when you do many measurements, and you eventually, or you can add them divided by m, eventually the whole thing just be single deterministic value, but the shape collapse direct direction like a Gaussian distribution with the variance. And if you divide the square root of m, it will be exactly approach to this variance of the single. Now, if you divide it by m, not square root of m, then the variance will shrink to 0. Okay, so now this is going to be a busy slide, and I'm going to spend a little bit more time to explain it. So what is now this third landmark called the large deviation principle? So this is a result based on first, we have what we call the law of large number. That is, right, the following way. Xm is the mean value of m repeated identical independent measurement. And if the mean value itself is a random number, then of course it has its own probability density function with a parameter m. When m go to infinity, we already discussed, it should just go into a delta function centered around a single point, which is the expected value. That's the law of large number. But then large deviation principle says you can actually have a asymptotic expression for this whole probability going to 0 except at 1 point, right? Direct delta function is 0 everywhere except at x star. And they go into 0 everywhere in this exponential form. So in our department, we probably know this is Bob O'Malley's favorite object. So they go to 0 with this m multiply a function phi for all the x. And this phi function has the following property. It is basically positive everywhere except this single point at x star. And everywhere else is positive, means this whole function when m go to infinity will be 0. The single point at which this function is 0, of course, made it very undetermined what's going on, but it turns out that is really representative where the delta is. So the existence of such a function, phi, and the simple form is what the mathematician usually like to do to prove it. But what we're going to do next slide is actually come up with a functional form to calculate it, right? Apply math, we don't really prove the existence, but we're trying to find the shape of the function. So why do we care about this phi? It turns out, in addition to we know this mathematical convergence rate, this phi function has a very interesting property. That is, now if you ask the question of this mean value with large M belongs to a set, which is inside the state space. And when M goes to infinity, it turns out the probability is completely determined by the minimum value of this phi function on that set. So now you realize somehow this function gives you a minimization, optimization procedure to allow you to determine what the value is going to be. So that is now you sort of sense the beginning of an entropy function shows up. And in fact, this is supposed to be a minus of the entropy function. So the optimization, minimization, maximization going to come into the story. And in fact, the mathematician in working this field do call this the phi function an entropy function. Of course, strictly speaking, it should be the minus phi is the entropy function. Now, in pictorially, this is really what it just this whole large deviation principle or large deviation theory tell us. This exponent function called a large deviation rate function because it tells us how fast this pink curve, when n increase, of course, getting sharper and sharper, become the blue, eventually become the green, eventually become a third function. And then all those things just go to 0 with this rate at every given x. And this phi function then have the following important property. Now, if you ask, what is the probability of this mean value bigger than a value a, away from the minimum? Then it's very clear because the probability really just dominated by the value with the lowest phi value. Anywhere has bigger phi value, the probability is exponentially small compared to this point at the corner here, at the minimum here. So therefore, at the end, when m is very large, you can ignore everything. You are definitively know the system conditional on the mean value is bigger than a will be actually here. So somehow this large deviation give you a very definitive prediction. If you just conditional on you know the system is bigger than a, the mean value, then you actually know for sure what's going to happen, because all the other possibility is even less likely. So therefore you can just ignore them. And that is why this function is useful. Let's go through a simple example. Let's consider a simple random variable, just take two values, 0 and 1, with probability p being 1 and probability 1 minus p being 0. And then again, we construct this sum and divide it by m. And it's very easy to show this is going to be a Gaussian distribution with the mean value exactly at p, and the variance now shrinking with the m. But we want to calculate the large deviation rate function. So what we do is we first ask, if I do capital M number of sample of this quantity, how many times I'm going to get in 1, and how many times I'm going to get in 0? Well, that will be just a simple binomial distribution problem. So the probability getting M number of 1s will be this combinatorial factor, and the probability p to m's power, and 1 minus p is q to this power. Now I'm going to replace the m by frequency x times total number of sample capital M. So everywhere the little m become capital M x, and I replace them. And then I'm going to let m go to infinity, or at least symptotically very large. And then you're going to get an expression, which inside the red bracket is exactly what I'm looking for, the large deviation rate function. Now you start to see if p equal q is all equal 1/2, then this term can be taken out. I start to see this x log 1 minus x log 1 minus x. This is the beginning of what we now write the Shannon's entropy, p log p, sum over all the possible states. So in fact, the Shannon's entropy is just a very, very special situation of multinomial distribution, equal probability, the large deviation rate function. Now, if you don't have the equal probability, then it's not supposed to be just p log p or x log x, the frequency, but you need to normalize them by the corresponding probability for each state. And this is called relative entropy, also called KR divergence in information theory. Now, the function I just showed here in the near x will basically give you a quadratic shape that is exactly the central limit theory tells you. And the position is exactly the law of large number tells you. But this function tells you exactly more than those simple behavior near the p, but it tells you a lot of these things, which if you do expansion through away from the mean value. That is why this whole theory is called large deviation. Okay, so now I'm going to basically trying to do the problem I just showed you for the most general random variable with a probability distribution P. The one I just showed you is a simple 0, 1 PQ problem, but how do we do a problem for the general random variable? And this turns out to be is a mathematical theorem called Cramér theory for identical independent distributed random variables. And it's if you do ID sample and construct the expected, construct the mean value, what is the origination rate? Of course, there's always more subtle mathematical condition I'm going to completely gloss over, not really go into the math to be rigorous. So here, let's assume the random variable x has probability density function fx. And since we are doing the sum, and they are random ID, so it is clearly what we want to do is taking advantage of calculating its Laplace transform, or it's called the generating function. Because when we do sum of random variables, their generating function is for multiplication. So we calculated the Laplace transform, also basically written this way, the generating function, and define and call it a psi beta. Then adding x is just become multiplying the psi. And after I take a log, that just ended with a multiply m times of this psi function. Oh, I'm sorry, there's a missing a log here. And then if I renormalize this whole thing by m, it just means the argument for the beta also be scaled by m. So now the generating function for this empirical mean, the mean value of the sample, will end with just this generating function. And then you can easily show this generating function, if you expanded a few terms near 0, will give you the law of large number and the central limit theorem, as expected. But let's just use the mathematical results I mentioned earlier as an answer. That is, the mean value, when m is very, very large, its density function can be expressed as exponential minus m as some function phi. Right? This is a mathematical theorem show you can do this. Let's just take it as a given and do this. And then normalize it in the denominator. And I'm going to plug this back into my generating function and hopefully find the phi. So I'm going to plug this in and calculate its generating function. And now I get into this step. If the phi is known, then I can just carry on the math. And we realize this is become a Laplace integral. And when m is very, very large, the only thing I care is about the minimum of this square bracket term. Or you can just do Taylor expansion near its minimum, get many terms. So if I call the minimum in the numerator is x star, but you also need to do the denominator, and now call it the minimum of the phi function is fx double star. Then basically I can just do this asymptotically. This is perfectly what we learned in 5.7.8. And then you ended with collecting the Gaussian integral, but the most importantly is this exponential term. And then you notice this function on the numerator has a minimum, but then the denominator has the function itself is the minimum. So therefore, this function together must have minimum is 0. So putting these together, what I really able to show you here is the generating function for the limit is eventually just equal the minimum of this function with this beta x coming from the generating function. So we can just basically do straight computation. Now, we do know if we calculate the generating function as a function of a beta, it's always convex. In fact, you can just check the derivative second time. The generating function has the convexity behavior, log generating function has the convexity behavior. Then we're basically able to use a result which Sasha will teach in his class. That is, if I have a function and its transformation become it's a convex, then this transformation, which is called the Ryan differential transformation, can go back and forth. That is, the generating function can obtain as a Laurent transform from phi, the unknown phi. Then the unknown phi now can actually just get as the Laurent transform of the generating function. Now, interestingly, this generating function, which if you still remember, has this integral form. Oh, sorry, here. Has this integral form with a log in front of it. In statistical physics, this is what we call a partition function. And in statistics, log of this partition function is what we call free entropy. Divided by a beta is what we call energy. And now if you start to do derivative respect of beta, in the statistical physics, you start to have this whole stuff about what is entropy and so on and so forth. So therefore, if I do the same thing, I can, the derivative of this quantity in physicist language, this minus rate function, which I call the eta, actually is entropy. Is the Gibbs entropy for something called a canonical ensemble. So I'm going to use this eta a little bit and use the phi function. They are really just trivially related by minus sign. So summarize these 3 mathematical slides is, if I take a probability distribution for a variable and multiply x, this is define a new quantity. This in physics is called free entropy. And then if I add a beta times x and find the minimum, that will give me the rate function. This is Cramér theorem. Basically, it gave you a procedure how to do this. But interestingly, all these quantity has meaning in statistical thermophysics. For example, the derivative of this quantity, which turns out to be exactly this minus, is actually Gibbs entropy. And then due to the duality between the psi and eta, I can just do this transformation backward and then relate the psi as a function of beta and the phi as a function of x, or eta as a function of x, back and forth, like here. And then now I'm going to generalize the things I just described to you. Instead of just think about one random variable, I'm going to think about a random variable form a vector with a k component. So now these y is all just y1, y2, y3, all the way to yk. And correspondingly, I have this beta variable is also going to have a beta1, beta2, all the way to beta k. And then for a given function of beta, the Laurent differential transformation is basically related to a psi beta to a eta y. Now, if this is the definition of the transform, I want to find the minimum of this argument inside the curly bracket. Of course, easiest way if it's differentiable, and if the minimum is actually inside the domain, then I can just do derivative, right? Now, if I do derivative respect to beta, what I get is going to be y plus psi prime, the derivative, equals 0, which basically means d psi is equal minus y d beta, which you write out explicitly in component would look like that. And then similarly, this equation, if I carry out the maximization through differentiation, of course, I will just get this equation, because derivative of this always says the beta should be exactly equal the derivative of the eta. Now, if this y turns out to be my energy of a system, which has a certain uncertainty, randomness, and the volume of the system, and the number of particles of the system, then the entropy change will relate to change is corresponding beta. Of course, at this moment, if you're citing the mathematics, we don't know what that beta means. It's just some parameter. However, it's now so tempting, basically realize this beta must be related to temperature, pressure, and chemical potential. And then even more interestingly, the math will immediately tell me there's another equation in the bottom. That is, now in terms of d beta and all these y, it should give me a d psi. And this relationship now in the recent textbook, because it's a generalization of Gibbs-Duhem equation due to Hill, so people started calling this new equation Hill-Gibbs-Duhem equation. So it looks like the fundamental relation in a Hill-Gibbs-Duhem equation really just coming from this large deviation theory. And the dual relation is clearly related, if you allow me to interpret these quantities as the physical quantity by this pair of relation. In fact, this is what Hill's nano thermodynamics, I just remind you again. He have this quantity with this one, and these two equations now looks remarkably similar to the one we just derived out of our large deviation theory. So what's going on? We believe Hill's nano thermodynamics really is about a small system and many, many multiple measurements. Because it's still small, so every measurement can have a different value. It's stochastic. If your average is a number, but with a sufficient number of measurements, you eventually have a statistical law. And that is basically large deviation theory of Cramér. In fact, there's more result. The y is related to psi through a gradient, and the beta is related to eta through a gradient. So these y and beta are widely known as thermodynamic variables, right? Temperature, pressure, volume. And amazingly, these psi and eta are exactly in the physics called thermodynamic potential. And of course, and these are vector fields, right? Y is multidimensional, beta is multidimensional, so this is actually a vector field. So is this. And now this vector field can be written as a gradient of a scalar. So this scalar is what we should call in applied math a potential function. And these are now, in fact, is being called a thermodynamic potential function. And in fact, if you study thermodynamics, there's a famous, many these things called a Maxwell relationship. What they're really saying is the derivative of the y2 component with respect to beta 1 should be equal to the y1 component with respect to beta 2, right? These are the cross equal sign to check whether a vector field is a potential field. We do that for vector calculus all the time. Is actually all those many different Maxwell relations in thermodynamics. And furthermore, if I write down these two relations and doing one more level of derivative, then I can get a matrix, is the Jacobian matrix. And these two relationships turns out to be 1-to-1. And the Jacobian matrix actually is just inverse to each other. And for a strictly convex function, of course, they are strictly basically positive definite. I jump through these slides. Now, what happens now if my system itself is big? So far, I'm basically talking about a many large number of measurements of a small system. But what happens if the system itself actually is big? Well, in that case, let me just borrow that statement from the earlier I showed from the Herbert Callan's thermodynamics book, which states the thermodynamic entropy should be a homogeneous Eulerian function of order 1 of all the extensive quantity, y. And then the Euler's theorem basically tells me such a function can be expressed, the order 1 function can be expressed as the derivative with respect to all the variables and multiply the variable. So homogeneous function has this property according to Euler's theorem. And note, we have the beta related to eta through that relationship earlier. Now, if you plug this in, you realize this is here, this is here, so this is 0. So in a macroscopic limit, if the system itself is large, this term is not zero. Therefore, Hill's theory now will be reduced to the classical thermodynamics with the Hill-Gibbs-Duhem equation become Hill-Gibbs-Duhem equation without a Hill term. Now let's investigate this issue a little bit more carefully. A homogeneous function of order 1, and we want to carry out its Lorentz transform. It turns out has some very interesting property. Let's just start with one variable. If it's a one variable homogeneous function, it's basically a linear function. So eta equal b1. And in order to do the math a little bit correct, let's assume start with y has a domain supported with a bound from y0 to y1. And so this is not a convex function anymore. This is a flat, straight line. But because we are constrained on this thing, we can still ask a question, what is the maximum of this quantity? And of course, it's all on the ends, on the terminal end of the function, on the domain. Basically, a picture shows that. It depends on y1 and y0. Let's pick the middle one, it's interesting. The y0 is less than 0, y1 is bigger than 0. Then the Lorentz differential transform is basically this wedged thing with the slope determined by y0 and y1. Now, let's say instead of y0 to y1 are actually in the whole real line. That is, y0 going to go to minus infinity, y1 is going to plus infinity. If that happens, what's going to happen for this wedged shape is it going to collapse into a vertical line with a single point has the support with the value 0, and everywhere defined is all go to infinity. So a homogeneous function, if you carry out Lorentz transform, it actually gives you some very singular lower dimensional object in the beta space. So here's an example. I jump through these 2 slides to show a 2-dimensional case. Basically use a picture to show. So now, if you have a homogeneous function of y1 and y2, that basically means the value on this circle will be exactly the same value on this circle, just scaled by a factor, right? This is a homogeneous function. Now, if you transfer the differential transform into the beta space, now if the y is actually not constrained by a finite region, but in the whole R, then this whole function in the beta space will collapse into a single curve in the beta 1, beta 2 space. A dimension just reduced. And in fact, that relationship, now you have a strict relationship between beta 1 and beta 2. Now, that basically means you have a strict relation between the pressure and the temperature. That is actually what a chemist, physicist, thermodynamic called the equation of state. There's a definitive relationship for a thermodynamic system between these temperatures and the pressures. And it's just come out of this homogeneous function, and you do Lorentz transform. So let me just summarize these stuff and see what we really seems like learn. Now, if I have a given small system with a certain probability distribution, it depends on reality, whatever that is, there's a probability distribution. And in fact, let's assume there's a density. In that case, if I take a log of that probability density, in physics, this is what people call a Boltzmann entropy. Now, taking that distribution, now using Cramér theorem, we can basically do repeated measurement on this small system, and then construct a large deviation theory. And that theory gives me a pair of quantity. One is very much like the free entropy, also in physics called the Matthews entropy. And another one is this Gibbs entropy as a dual pair. One is defined in this beta space, another one still defined on this original random variable space. And they are equivalent. You can do back and forth again and again, and they're convex. Now, if you decide to make the system itself is very large, then this duality symmetry disappears. on the one side, one of these quantity become sub-extensive. In fact, they start to collapse in a lot of places, become a lower dimensional object. And on the other hand, this eta function become a homogeneous function, which both numerator and denominator here go to infinity. That means you can use the L'Hopital's method just to derivative. That actually gives you the beta. So it looks like through this large deviation theory, for a small system, we actually gain some kind of duality symmetry in thermodynamic behavior. But now if we really go back to the macroscopic system, this duality symmetry is lost. And of course, the classical thermodynamics did not have this middle step. So therefore, we always get this non-symmetric result with the Gibbs-Duhem equation seems like strange, as I showed you earlier in the Wikipedia. But the Hill theory really now putting this middle step back in, and he in fact discovered this duality, even though he didn't do any math like this. He was using a completely different kind of logic based on argument and intuition and traditional thermodynamics. And these two functions are convex. And now in the macroscopic limit, these are homogeneous functions, and this becomes a sub-homogeneous. This becomes extensive quantity, and this becomes sub-extensive. So, in conclusion, the thermodynamic structure presented here, and we do assume there is always a probability distribution to start. We already know distribution. That is basically theory of probability, we always assume. But I never mentioned anywhere in my talk about what is equilibrium, the kind of concept classical physicists need. Neither, because I don't even do dynamics, I didn't even mention anything about ergodicity, which is another nagging issue, recurrent issue in classical statistical physics. So without this assumption, the kind of theory I described, the mathematics I described, can actually apply to many other systems. For example, a living cell, a single cell, and you have to do a lot of measurement on a single cell. This theory should be applied, could be applicable. Of course, if you have a system itself is very large, then you can basically treat them as has many, many small parts. Then you don't have to do repeated measurement. You just do one measurement. It's already add all those things together. That is what the old traditional thermodynamics is about. And in fact, this idea fundamentally was already in Boltzmann's work in 1877. He is considered to be the presage of large deviation theory. And this whole mathematical description, we hope, actually gave a much sort of precise and hopefully more useful mathematical description of traditional classical thermodynamics. Because right now, the thermodynamics, as I mentioned earlier in the beginning, is not very mathematical, and there's a lot of stuff, and our applied mathematician doesn't really get into there because it's just sort of not our kind of thing. And it's also interesting to show now we actually have one dimension in this thermodynamic behavior that is a small system, but you can have many, many measurements, and there's something emergent with laws and then can in that limit. And then this duality symmetry certainly seems to me is very interesting and must be important. And then its breaking lead to the macroscopic thermodynamics seems like a pretty interesting observation. So I just want to basically say one of the things face modern applied mathematics is the twin challenge between scale and complexity. You know, when we do larger and larger scale computations, all kind of things, we're basically dealing with these two things. In terms of a probability, we turn these two sort of adversary factors. You know, it's hard to overcome, become advantage, because you want a probability space is basically exactly have a huge about all the possible measurements, right? In fact, n has to go to infinity. So somehow probability turn these two very adversary factors become advantage. I jump through this. And this work is basically a collaboration with Professor Julia Lu at UNC, Chapel Hill. And here are people in my group. I constantly learn a lot of math from them. And one more thing is, this whole project really started with this group of people. We want to read the nano thermodynamics, the new sort of Hill thermodynamics. There's a new book came out, just published. We decided to read that book. And through reading that book, we realized maybe there's even something new. Thank you.
Thank you, Hong, for such an informative seminar on the foundations of thermodynamics in terms of the mathematics and the stochastic processes and equations. And probably for students, it connects many of the pieces that they're covering or covered in stochastics, dynamics, and so on. We have time for questions, so let's transition to questions. Feel free to write those questions in chat, and then I will read them, or type hand in the chat. And yeah, I'll just let you turn on your microphone and ask your question.
So Hong, I don't know, it's not a question and I'm not even sure that it's a comment, but I remember seeing a talk by Barry Simon in which he has these things he calls spectral theory gems, where you have a symmetric tridiagonal matrix, and he gets surprising relationships between the entries of the matrix and the eigenvalues. And there's kind of really intricate formulas that they can derive that relate these two things. And recently I saw a talk where he derived these formulas from a large deviation principle from random matrix theory. And
okay.
so it somehow seems that, I mean, at least the essence of, there's some piece of that's connecting to this idea where you have a couple sets of variables and a large deviation principle is relating them. Just
cool.
Yeah, I mean, it's just a comment. I don't know if it's really related, but just a thought.
Well, certainly, if it's a large deviation series, they're related somehow.
Right.
All right, there is a question from Michael McCarthy on chat. Is the assumption of a probability distribution related to an equilibrium assumption?
No, because clearly the equilibrium assumption in physics has much more than just having a probability and being stationary and invariant. It actually have to involve in a more Markov sort of in a dynamics, there's no flux. So we can have many systems, and the easiest way is set up a metal bar with 100 degree on the one side and 0 degree on the other. And then you're going to eventually have a very stationary temperature distribution across the metal bar. That will not be considered equilibrium by physicists or any so-called equilibrium statistical physics. But it's clearly a stationary with whatever the probability forever there. So therefore, all the probability theory you can apply, but it's not equilibrium.
Thanks. Additional questions? Cool. Okay. It looks like no more questions, and we are approaching 5 p.m. So I would like to thank Hong again, and I'm putting the clapping reaction in Zoom. Yeah, thanks so much. And I would like to mention the next talk in the series. This will be by Tom Trogdon. This will be in 2 weeks from now, so November 5th. And Tom will talk about the Wishart ensemble. And it involves several scientists, mathematicians with kind of like hard to pronounce last names. So Tom will introduce us to how to pronounce all these names and also the content of the research ensemble. So yeah, thanks so much, and we'll see you in 2 weeks.
Thank you.